pick one and say this is the best one and start using it in WebRTC. Because WebRTC does do the energy level extension. And the energy level extension, in addition to the energy level, the top bit, most significant bit, is supposed to be the VAD. And the VAD should not just be, is the energy level greater than 80?
Sure. Yeah.
It's supposed to be actual speech VAD. And
I also know some people start the month with transformer-based architectures for this that might. You can imagine a transformer would be pretty good for separating this, but it might not be fast enough. Get the large or for either encoding decisions.
Yeah, the Inopus, the speech music detector is a neural network. It's a pretty small one.
I think even traditional neural networks without transformers would be easy to detect.
Right.
Classifier, just to say,
Right.
is it active speech or not?
Renewable. I think it's nice. Well, thank you.
Welcome, everybody. We'll just give it a few more minutes to let people lingering in the break area to come in if they want.
Seriously? We always have hope.
We only have about 90 of our 120 minutes allocated, so give it a few minutes. I think we'll probably end early today. Give you an early dinner if you want, even though you can't get into any restaurant before 8:30. You may have a late lunch if you want after this. Yes. Okay, welcome everyone to MLCODEC, Machine Learning for Audio Coding at IETF 123. So first of all, please familiarize yourself with our IPR policy at the IETF, namely that any contributions here, and that means speaking at the mic, participating in discussions and activity, presenting, writing drafts, reviewing drafts, all those activities, we expect you to disclose any IPR that you're aware of, whether it's your own or others. Please read through these BCPs for more details. And we also have a code of conduct. If you believe that you have not been treated professionally or have witnessed any unprofessional treatment, please contact your ombudsman, and they're available on the IETF.org site. Some tips for meeting logistics. Everyone in the room, please make sure to log into the Meet Echo tool, probably the on-site tool. That'll give us the automatic blue sheet registrations. Please also, if you're using the full client, keep your video and audio off while you're in the room. And remote participants, use the full client and also keep your audio off until you're speaking at the mic in queue. In room, also use the tool in the on-site tool for joining the queue. And use a headset if you have any echo issues. So we can look at the agenda. Let's see if there's any note takers that are available. We don't need a Zoom relay, but anyone available to take notes? It'll be very terse, just the highlights, main points, any actions for the chairs. Okay. Thank you very much, Benson. Our agenda today, we have the Opus extension mechanism. Tim will be presenting that, followed by the deep redundancy extension from Jean-Marc, and then the speech coding enhancements from Jan, and then the new work for scalable quality extension by Jean-Marc, and then finally a speech quality intelligibility testing battery from Laura. Any comments or bashing on the agenda? And we should end early if we stick to it. Okay. Tim, you're up. Would you like me to share, or do you want to share?
Yeah, go ahead. All right, so this is talking about the Opus extensions draft. Next slide. Current status is that the 04 version was published last night. I don't expect that anybody has read it already, but it is out there. So that contains the change we discussed in Bangkok, talking about frame separators with an increment of 0. And also includes a suggestion from Mo from that meeting to clarify that frame separators, the non-zero increment, are not repeated by the repeat these extensions mechanism. Other than that, I did a bunch of edits to improve clarity and precision, following some advice from Mark Harris. And so hopefully I improved clarity and made things more precise. So you guys will read that and tell me. But next slide. Other than that, I'm not sure there's any actual work to be left to be done in this draft, so we may be ready for last call, but you guys tell me.
So has Anyone, I guess no one has had a chance to review Rev 4. Does anyone have anything that was outstanding on the previous version that they thought would not be ready for last call? Okay, none in the room or online. So I think with your changes, Tim, I think we probably are ready to start a last call this week, and we'll probably let it run through at least 2.5 weeks after everyone returns back.
Yeah, all right, sounds good. The last slide's just a backup, so that's the presentation.
Thank you. Jean-Marc, would you like me to present or you want to share?
No, please share. So this is the deep redundancy for Opus. We're now at version 0.4. Can you go to the next slide, please? So in terms of technical changes, since the last time, mostly there's been a few improvements to the training procedure. So a better schedule for the training with the lambda, so the rate distortion term for the initial state that gave us more initial vectors, overall better quality at the same bit rate. Also enabled soft quantization from Yan that makes it easier to do the weight quantization with less loss. Overall, relatively minor changes. In terms of robustness, we started training a little bit with noise and reverb augmentation. I still don't think it is very useful to be robust to noise and reverb because basically everyone removes that, but just to be on the safe side, it doesn't hurt anything, so we gain a little bit of robustness there in the training. Another thing I did try and thought it's useful to report negative results as well, which was a denoising network. So training Dread to input noisy features or reverby features and have the decoder give you the clean. And if you test Dread standalone, it sounds a lot better. And if you test it with packet loss mixed in Opus, it sounds absolutely terrible. Because if you have noise and you try to do denoising, then suddenly your noise goes up and down, up and down. So I thought I'd point this out. This is apparently not something we want to do, even though for a regular codec, it might be a good idea. So the new model, I can train with all of the above. It performs slightly better than what we previously had, despite being about 3 times smaller. And all of that is available in the EXP Dread NewConf 6 branch. It is purposely not in main, mostly because a lot of people are just testing Dread, and we don't want to necessarily break compatibility all the time. So it's on a side branch, but everything's over there. Next slide, please.
As an individual, clarification on this. It's on an experimental branch, but you expect this to be incorporated in the final stand. You expect these new weights that are 3x smaller to be the final weights?
I do not expect these weights to be the very final weights. This is something we should probably discuss about exactly how we come up, but there should be very similar to what we end up with as the final weights.
But you expect that the final weights would reflect this shrink, right?
Yes.
Jonathan, do I recall correctly, you were using a temporary extension ID? So will the
Correct.
new weights use a different extension ID?
The new weights will have the same. So there's an extension ID, and then there's another byte that identifies the version of this experimental extension, and that's going to jump.
Okay, and that's going to go away when you have the final one?
And when we have the final one, we'll use the real thing without. Right now, we actually have 2 bytes. There's like a D byte that says this is dread for this experimental extension, and the next byte says this, which version of dread it is. Those 2 bytes are going to go away.
Awesome.
So next slide, if there's no more questions. Okay, so this is essentially what this new model looks like. It's much smaller. The encoder has about 200,000 weights, about 245 kilobytes in size. The size is a little bit bigger. There's a little bit of overhead. There's a few weights that cannot be quantized to 8 bits, but still much smaller than the 1 megabyte we had before. The decoder is now at 290,000 weights, 365 kilobytes. Again, much smaller. And I'm repeating it again. This is not in main. You need this EXP Dread NewConf 6 branch if you want to test that out.
A quick question as an individual here. Is the computational complexity of the encoder and decoder decrease proportionally to the weight change here?
Yes. The complexity is essentially one multiply and accumulate per weight per frame. That's what happens there.
And can you clarify if this reduction in weights and complexity came from like architectural changes or just sparsity in the weights, or
it came from a few different places. More sparsity in the GRU layers, sparsity in some of the extra layers, and also the convolutional layers used to be these big non-sparse convolutions. We added a fully connected layer in front of it to reduce dimensionality because some of the inputs to those convolutional layers were pretty wide. So between that and the sparsity, it made a big difference without affecting the model much.
is that commentary captured anywhere? Because I think that'd be very useful to have, even if not permanently in the draft, just on list or just something to inform. It's a pretty dramatic change, so something to inform the dramatic change I think would be useful, either in the draft or on the list if you don't want to permanently put it in RFC.
Yeah, okay. Next slide. Okay, so the main change, it's partially reflected in the draft, I believe, but it needs some more updates. But essentially, I think the test vectors are now in a better shape than they were. So first thing, so this is essentially what I'm proposing for the test vectors. One is, first part of it basically is to have this binary format. So Dread, we'll use the entropy coder, pack a whole bunch of frames together in there. And now if you download this Dread test vectors .gz, essentially what you have is a set of vectors. We have the compressed version. There's a Fargan demo tool that can be used to decompress. So it gives you a file with the actual features in there. And then there's a Dread compare tool now. It's all in main and in that new branch. And so the Dread compare with the minus features option will compare the reference decoded features. So they're decoded with the float, weights, full precision, everything. And you compare that with what you're getting, and the compare tool will tell you if this is essentially compliant. There's a minus threshold that computes 3 different metrics. A sort of MSC-like metric, mean squared error. The max feature error, or essentially like MSC but biased towards the larger error, and the pitch error. So if all 3 pass, then you pass the test vectors. There's multiple test vectors as well. And there's this test in the test directory. There's this dread vectors.sh script that will run everything on the test vectors, just like the run vectors tool was for the original Opus. And so with that, you can verify if it passes the test vectors. The way I've tuned these thresholds there is to be slightly more strict than the quantization noise you get at Q0, which is the highest quality quantizer. So if you pass these, then you're not the limiting factor. You know, the quantization is still the limiting factor, even at the highest bit rate. So that's for testing the actual DNN that does the dread decoding. Next slide, please.
Real quick on this, before I think you said that this was going to be normative in the draft. So does the current version of the draft already point to something or already incorporate in these vectors somehow? Or are you waiting for a resolution of where the final storage is for both the weights and the vectors and everything that's going to be normative?
So the draft already has some of this. It doesn't have like the full scripts and everything, but it's actually, I mean, yeah, no, the draft still needs more work. Sorry, with respect to these test vectors, it's essentially work that I did after the deadline.
Okay.
So it just alludes to test vectors, but doesn't have the details in there. I'll update it.
Okay.
To
So
match all those.
in your update, you'll describe the test vectors in more detail, and then reference something that maybe reference your current repo for now, but something that may change when we decide the permanent place for the archival of the weights and the test vectors. Everything normative for the spec that needs to reference.
Yeah, essentially, it's going to be what's going to be normative. The dread compare tool, I think, will just fit in the draft. It's very small. I think that there's no issue there. The actual dread test vectors file, that one needs to be published somewhere. We need to figure that out. That's the real one.
Got it.
So that is essentially for verifying that the dread feature decoder works. Next slide. There's more to the test vectors. So next thing is the vocoder itself. We've discussed different ways, like how should we standardize the vocoder, and my proposal at this point is that we just have it with test vectors just like a standard decoder. So in the same test vectors file, I also included the cleaned features for the speech files we had. And next to the clean ones, we have, the clean features and the original audio. And the Fargan demo tool, again, with the Fargan synthesis option, will run the Fargan vocoder to synthesize from the features. And of course, if you wanted your own vocoder, you would use your own vocoder there. You wouldn't use Fargan demo. And the dread compare tool has an audio switch that will compare the clean audio with the synthesized audio. And it has a bunch of error parameters, essentially average, peak error, and pitch error. And if all of those pass, then your vocoder is close enough. And essentially the thresholds I have there, they've been tuned such that a badly trained Fargan vocoder, like with just one epoch, will pass the test vectors. Whereas if you use Fargan, but just shift in time a little bit or do something really bad, it fails. So it doesn't need to be high fidelity or anything. This is for redundancy. It just needs to be like vaguely in the same ballpark as what the original audio was. I see. I saw Tim wanted to say something.
Go ahead, Tim.
Yeah, I just wanted to ask how the two models, the old 1 megabyte model and the new model that's a third of that size, compare against these thresholds. Like, would they both pass?
Yes, they both. I mean, they both pass with different test vectors, obviously, because the format ends up being different. But yes, they both pass. Sorry,
Oh,
they
okay.
both pass.
Okay, so they would not pass the same set of test vectors.
No, absolutely not. The format of the new model is completely different. They're not compatible in any way. The features mean something different. They may be in different order and so on.
Okay, good.
I
That was
have
my
test
question.
vectors for the new model as well,
All right. All right. Thank
but
you.
they're completely different. But yeah, both work with the same threshold, which should be good. So this dread vectors.sh script that I mentioned also includes the vocoder test. And yeah, the thresholds have been set relatively lax in there, just making sure that the vocoder is correctly aligned and producing something that sounds like the real speech. Next slide, please. Oh, sorry, there was a
Go ahead, Yusuf.
question in the queue.
Yusuf Işık from Cisco. When you compare the two models, other than these metrics, do you have like subjective tests on quality to compare them? And second question is, if this is not the final model, do you have any major changes planned already? If so, what are they?
Okay, so the first question was, I'm sorry, I forgot the first one.
The quality when you compare the two models.
Oh, how to compare the quality? Yes. So what I'm using to test right now is actually objective metrics, which I generally do not trust. But in this case, when you just change the features for some with no changes that are supposed to be, psychoacoustically relevant, it should be good enough. It just tells you how close your features are. And so the new model is actually slightly higher quality than the original 1 megabyte model, probably mostly due to the robustness changes that we did. Even though I'm not testing with noisy speech, the noise just helps generalizability, so it seems to help a little bit. It's not day and night. You probably would not, just by listening to it, you probably would not notice the difference.
Can you clarify one thing, Jean-Marc, on that first question? Can you clarify one thing? I assume that these test vectors are just binary pass-fail, right? They don't give you any kind of comparative or qualitative result, right? It's just a binary pass-fail result, right?
Yes. And also, they do not tell you how good your quantizer is. They just tell you how close you are to the reference quantizer. Like if you start with the clean features, you quantize them, they're quantized at all quantizers between Q0 and Q15. So they're quantized and they give you quantized vectors that do not fit quite the original. They have some error. And that's what you have in the test vectors. And then you start from the decoded and you have your own implementation and you compare the two decoders. At this point, you do not, for the dread vectors, you do not compare with the original, you compare with reference decoded and your own decoded. So they're going to be very close.
Sorry, go ahead to a second question.
Yeah, so in terms of upcoming changes, I'm doing like a last round of toying around with extra sparsity, but I might gain like 20, 30 kilobytes or something like that, but no 3x anymore. And so we'll just need to figure out, when and exactly how to do the final model. But this is something that, should happen probably like in the next month, training the very final model. And anyone who would like to get involved, be checking what I'm doing or trying to repeat or test or whatever, please let me know. There's been some discussion around that.
Because it sounds like
Otherwise,
there's now some more feedback from listening tests on the prior generation model. So do you think that that might result in some additional changes to the training process or data that's going to training?
you mean the listening tests themselves?
Yeah.
So I think it's probably good if we can just like double check that what should be the final model is actually good, like verify that somehow the objective metrics haven't like completely led us astray or something, which I don't think is the case, but it's always a good thing. And also like just documenting how the final model performs. Like I think that is, in terms of characterization, that's useful as well. Next slide, please. So another part of these test vectors is the integration. So these are, let's say, not, I think those should be like a should or something, or we can discuss exactly what they do, but these test vectors essentially have Opus Dread bit streams. So it's a bit stream where you have the Opus packets, you have the Dread in it, and in the test vectors, we've actually cleared some of the packets are just empty. Therefore, the Opus demo decoder will treat them as Dread. So that's a way of simulating Dread in that circumstance. And so we have the feature, so like we have this Opus demo -D tool that will decode Opus plus Dread. So the output is going to be a mix of Opus and Dread in there. And again, this Dread compare -audio will compare with the reference. So that's going to be the original audio. And again, obviously, it's been coded with Dread with Opus, so it needs to, it's not going to be extremely close, but we've set some thresholds that will verify that things appear to work, or be close enough, and no huge mistake in the way that the two are integrated. Essentially, like if you mess up the vocoder, the transitions, or something like that, it should show up. I think it's hard to make these like really foolproof. So my hunch would be to say that it's recommended to pass these test vectors, but I'm not sure I would go as far as making them musts like the two previous ones. But I'm open to suggestions there. Any questions? Otherwise, can go to the last slide. Sorry, Tim, I see.
Go ahead, Tim.
Yeah, so at least in the original Opus draft, handling packet loss was entirely non-normative. So I think keeping this at no more than optional or recommended is a good idea.
Yep, fair enough. And also in this case, we're not talking about matching, like the comparison isn't even with what the current Opus decoder decodes, it is with the original. So this is not about saying you should be doing it exactly this way, just like your audio sounds vaguely like the original that it should look like. But still, I would go with optional.
Yeah, just to clarify, recommended is usually like a should, with an exception. Here's some special cases where you would not. But sounds like you're not recommending it. You're just saying that if you want to do it, you can, but most implementations don't necessarily need to.
I guess the way I understood this is the concern here, I think it's that that it's quite easy since dread concealment is something that, you know, is an exceptional case, that an implementation could mess it up completely and they may not notice, or unless you actually test with packet loss. So that your goal is to just provide a tool to help people not make that kind of error, right? That, like, it doesn't even decode the dread. Or
Yeah, or just, you know, like computing offsets the wrong way, that sort of thing, like, and not aligning things properly, like that should show up. Whether it should be a may or a should, I'm open to suggestions. I don't have a strong opinion. That's why I put both here. Any thoughts or preferences? Tim, are you still from the previous time, or?
No, I had a new thought, which was, yeah. I mean, I think we all know the definition of should in the IETF, right? But I feel like that's the right level. But you know, you want to give people an out, because like there are some implementations, as Jean-Marc said, like might not need to handle packet loss at all, right? And we shouldn't be forcing them to go try to implement something they're never going to use.
Say you should test, but maybe it doesn't matter if you pass as long as you know that what you're doing. Right?
Well, I mean, if you don't handle packet loss, you're not going to be implementing the spec to begin with. So I think that one is. It's more about like, maybe at some point, like you make a really good implementation of dread, like much better than what the current code does, and now for whatever reason the test failed, but it sounds so much better. Like that would be the case that I see.
Yeah. You can have errors in both directions, right? But yeah, I feel like it's maybe a little bit too much to say that this is the way it has to be forevermore.
Yeah, it's definitely not a must, I think. It's just like may versus should.
So do you have the guidance you need to decide this?
Yeah, I mean, I think we can start with, if there's no strong opinion, I might just have a should, and if at some point someone shows up and goes like, oh, this is bad, you know, we can downgrade it. But so I guess we can go to the next and last slide. So open questions. So, you know, we still need to resolve, you know, where to publish the weights, where to publish the test vectors. As I mentioned, we're going to be ready probably within a month to produce the final weights. So anyone who would like to participate or give input in there, like, please do so. And in general, like, is there anything I missed? What else do we need to finish this off?
Okay, so for where to publish the normative aspects, I think the chairs will take an action. We still haven't closed off with the AD, our AD changed, and we never got guidance from old or new about where best to take this. So I think we'll take it to a few more people, find what the best archival place is for this. I don't expect we'll do what Opus did. We won't be base 64ing a bunch of binary weights in the text. We'll do
1/3 of them now.
Okay, yeah, so only a couple of thousand instead of tens of thousands of pages. So we're still taking the action to figure out what the final reference location will be. And it will be both weights and test vectors now, right?
Correct. Yep. For Opus, we had the test vectors in the proceedings of some meeting or something, just to have a permanent link. So,
yeah.
Not saying it's ideal.
Yeah, no. You'd never reference proceedings in an RFC, so that wouldn't fly either. Yeah.
I think we do actually in the Opus draft, in the Opus RFC, but
Yeah, I don't
Yeah,
think
okay.
that Opus was a very frowned upon from a process point of view. We don't want to repeat that.
Yes.
So we'll take that first action from the chairs to close off where you got to document this, so you don't have to worry about it. The second one, I think, is more for you and the work group to decide when is good enough, and I think maybe we should come back to that after we hear from the final presentation about subjective testing with DREAD, and we'll see whether or not the when question is, are we done or do we need more time?
Tim?
Yeah, I just wanted to add that I'm not sure that proceedings URL was actually as permanent as you might have hoped either.
Nope.
I think some change in the software, like added some extension or removed some extension or something weird was the last time I tried to use them.
Oops. So anyway, that's all I had for DREAD.
Thank you very much.
Thank you.
Jan, you're up. Would you like me to present?
Yes, please. That would be great. Okay. Okay. No, I don't think that's the one.
Sorry. Too many quality. You want enhancement, not quality. Right.
That looks better. So I will give an update on the Opus speech coding enhancement. This time entirely about bandwidth extension. At IETF 121, I already talked about the blind bandwidth extension algorithm, and now it's fully integrated. So I will give an update. And next slide, please. Okay, so on the algorithmic side, the non-guided wideband to full band speech extension algorithms BWENet. That's now fully integrated into Opus, landed this week. It requires both compile time and runtime activation. The first one is the configure flag. The second one is a flag to Opus demo. Once it's enabled, it's tied both to the DEC complexity, which has to be at least 4, and it will only be active if the output sampling rate is 48 kilohertz. And in addition to that, one of the following cases must be satisfied. So the mode is either silk only and the bandwidth wideband. It's not applied if the bandwidth is narrowband, which would be the other case here. Or the mode is hybrid, which means that CALD is supposed to provide the high band, but no data is given, which is the case if you have PLC or if you are decoding redundancy. Next slide, please. So the full integration looks like this. It's the bandwidth extension algorithm. It's a optional replacement for the resampler that does 16 to 48 kilohertz upsampling. And it basically operates at the very end of the silk decoder, which has the implication that you can operate on just the silk output. You can apply lace or no lace enhancement before. Also, classical PLC, Neuro PLC, and DREADS decoding, that's all done in the silk decoder. So it will extend all of those alike. I put together 2 examples just for illustration. Next slide, please. So this is an example what happens if you decode a wideband payload on the first side, if you don't enable the bandwidth extension. And on the right side, if you do enable it, you get an extension of your spectrum. I can also share the files over the reflector if people are interested in listening. And next slide, please. The second example is about DREAD. So what you can see is if you're operating in a full band and you have a lot of packet loss, in this case it's 90%, then DRED decoding uses a wideband vocoder. So you will get these holes, and it kind of sounds very inconsistent that the bandwidth is reducing and going up again. And with the integrated bandwidth extension algorithm, it will always kick in when you do have loss, when DRED decoding is applied, and it will elevate the vocoder output to full band. That's it on the algorithmic side, I believe. Next slide, please. Regarding the draft, there have been two very minor updates. The first one, I incorporated a proposition by Mo from a meeting before last one. On the interoperability criterion, it said something like if a Silk encoder produces a payload that can be decoded into a recognizable production of the signal by an enhanced decoder, then it must also be decoded into a recognizable representation of the signal, or reproduction of the signal by a legacy decoder. And I added the suggestion to replace recognizable by human recognizable to make it a bit more specific. Other than that, the current draft already distinguishes between extending and non-extending Silk enhancement algorithms. And apart from the general requirements, such as subjective listening and so on, it does not specify any specific requirements for the extending Silk enhancement. And now we have actually a first example of such an algorithm. And so it's time to think about what requirements to put in place. Still, I'd like to stress that so subjective testing is one thing, but the requirements that would be mandatory, that's rather like a guardrail to prevent that unintended things happening when integrating new methods in the future. Next slide, please. One of the challenges is that blind bandwidth extension, it's blind, so it's not a very well-defined problem. So if you have a low band signal, there are multiple plausible extensions. So you cannot really say what the right one is, although all of them will sound plausible and better than the original. Also, I think every bandwidth extension should be seen as an improvement. So even if you would just go from 8 to 9 kilohertz or from 8 to 12, that would sound better. But what follows from this is that you can actually not demand very much from the high band. So the best thing that you can do is you can say, apart from subjective testing, for adaptive testing, you can say something like it should not be worse than doing nothing. And the proposal at this point is that for this extending enhancement algorithm, for the low band, we could actually use just the same requirement as for the non-extending algorithm, which means it's going to be downsampled to 16 kilohertz, and we run the low band test on the downsample result. And for evaluating the high band, the idea would be to implement something that does a not worse than doing nothing test. Next slide, please. And I put one first example into place. The assumption is basically that if you have a good bandwidth extension algorithm, which extends the signal into something that's plausible, then at least the energy in high band over time that will correlate well with the reference signal, or the energy of the reference signal. Whereas if you have a faulty bandwidth extension algorithm, you will have somewhat weaker correlation. And this means that if you measure distortion on power spectra, what will happen is the distortion will be lower between the good extended signal and the reference compared to unextended and reference. Whereas if you have a faulty bandwidth extension algorithm, then the difference between extended and reference will be worse than between extended and unextended and reference. And such a method is implemented on the Opus main branch in the highband eval.py script, and I put together an example to illustrate how it works. Next slide, please. So you basically see 4 spectrograms here. First one is the original. The second one is 8 kilohertz low pass, so that's doing nothing. Third one is the actual bandwidth extension algorithm that's currently implemented. And the last one, that is a simulation of a bad bandwidth extension. So what it does, it's just the original, but it will flip the high band in time. It's also just an excerpt of a longer signal, so you don't exactly see the flip, but you can see there is some high band energy where it's not supposed to be, and there is some energy missing where it's also supposed to be. On the left, you see 4 bands, which are actually the Opus bands that follow a Bach scale. And you can see if you compare original to original, the distortion is 0. Then if you compare to the low-pass filters, it goes up. For the bandwidth extension algorithm, all of these numbers go down. And if you do a temporal flip of the high band, all of the numbers go up compared to doing nothing. So that part works out. And I tested it on a subset of the EARS dataset. And so to say, the bandwidth extension always satisfied the requirements, and the flip one always failed. So that looks promising. Next slide, please.
Question as individual
Yes.
first.
Please.
Can you describe what your distortion is?
It's basically you take the power, you take the energy in bands, then you apply some noise floor, depending on the reference signal. Then you have a power of 0.25 or so to convert basically to loudness, and then you look at the L2 norm over time. So.
And all this is specified in the latest draft?
It's not in the draft yet. At this point, it's not yet about draft update. It's in the reference Python file in the main Opus main branch.
But you plan to add this to the draft? This will be the way that they evaluate whether they're correct or not?
I plan to add it to the draft pending feedback. So the main purpose is now to get feedback and see if people object to this general approach or are supportive. And if people are supportive, I will add it to the draft.
And what is the significance of that right case, the synthetic bad case? Are you trying to use that as a reference number that you should be below, or?
No. This is just, I mean, I put this assumption in place that if you have a bad extension, it will actually fail the test.
So it's just illustrative.
It's just illustrative. The actual test is,
Yeah, the comparison
Please,
point is
correct.
kilohertz low pass.
As long as you're roughly in that ballpark, you don't have to be strictly lower, or
I mean,
strictly lower,
you
or
could,
just roughly?
that's a pathological corner case. We could probably say, I mean, if you say lower is not permitted, then you're, I mean, doing nothing is excluded. So to remind you, the specification says subjective testing, please, and significant improvement for at least one operating point. So it's not a hard requirement, but it's a should requirement. And here we can go with smaller, or we can go with, I mean, at least, or at most, or I have no strong feeling about this.
Okay. Yusuf?
Yusuf Işık, Cisco. Are you proposing this testing methodology just for this change or for any extending enhancement technology? And I would like to get your comments on generative speech enhancement bandwidth extension methods where they can create plausible high frequency, but the correlation with the reference might be low, but it's still very good speech. And sometimes it can create speaker morphing. So when you test the low and high separately, maybe it's good, but when you combine, people might feel differently.
Yes, okay. So let me answer one question after the other. The first one is there is at the moment no plan to specify any of the enhancement algorithms. So the test would be to facilitate adding enhancement in the future. So it should apply to all of them. Regarding generative methods, it's actually not high band correlation that I'm looking at. It's energy correlation. So even for this case, I mean, it's also basically a generative method. So even here, if I would compare the signal in high band, they would be basically uncorrelated. But if I use a spectrogram and if I look at the energy, they start to be correlated. And I would assume that no matter what method you use, that should always be the case. It basically just says if there is something in the reference signal, there will be something in the extended signal. So if you have a fricative, there is supposed to be some energy. And regarding your question that, of course, there could be artifacts if you combine a high band and a low band. Yes, I'm not claiming that this test will guarantee that you have a good bandwidth extension. It's basically, again, a guardrail. If you want to do a quality evaluation, you have to do subjective testing. And this is recommended. Does this answer your questions?
Yes, thanks.
Okay, thank you.
Jean-Marc, go ahead.
Yeah, I just wanted to just reiterate and clarify that essentially this new proposal is because we were completely enhancement agnostic in the original draft, just saying how you should enhance within the existing bandwidth. And this is an extension of the document that says, if you want to go to a wider bandwidth, this is how you're going to, this is what you need to satisfy and how you need to go about it. And it's different than if you keep the same bandwidth. So that's just an extension, but it's meant to be work for like generative or any other kind of method there.
So would you expect to use the same kind of standard for a narrow band to wide band extension?
Oh, let's not go there.
Okay.
This is wide band and beyond. Narrow band is, let's not do that.
Yeah, because my follow-up question would be stuff like S versus F confusion. And
Yes.
like that.
No. Maybe
Yes.
we need to clarify it if it's not already there.
It is
beyond
clarified.
wide band. Okay, great.
I mean, it is clarified that it's wideband to higher bandwidth extension. Yes.
Yeah. Okay.
Okay. There are no further questions. Then yes, next. So in terms of next steps, so the model that's currently integrated, it's the float model. Reason is that, as Jean-Marc mentioned before, you want to have soft quantization during training, and that was not included for the very first model. So the next step will be to quantize the model. That requires retraining or fine-tuning, trying to find out which one it is. For the standardization part, as I said, I'd like to have feedback on the high band evaluation and whether people think that's suitable. A carryover that I still have to do is to add PLC masking to the low band, the wide band test. And then the last point is actually for full band, it's essential for this test that you have full band test material. And common voice, what we use for low band testing, that's just super wideband, so that won't work. The EOS data set is actually pretty nice. It stands for what was it? Emotion? No, expressive anechoic recordings of speech. There are even sneezing noises and so on in there. So it really covers a huge range, but it's Creative Commons non-commercial. I'm not sure whether that means that we can't use it or not. Otherwise, I have to look for something else. Yes, so these are the next steps. And that's all I have for this meeting. Thanks.
One question about your algorithm.
Yes.
When you do quantization experiments, are you also going to experiment with things like Jean-Marc to try to sparsify some of the layers?
I did this once for no layers and there was no evident benefit. So the quality always scaled with the number of weights, no matter whether I change dimensions or add sparsity. So the mechanics for that is there. One can do it. I'm not sure whether I will give it another try, maybe.
So don't expect any 3Xs.
I mean, a 3X, I mean, that one is already, it's like 140 megaflops. I'm still thinking about shrinking it a bit. It will go down a little bit, and but we will end up somewhere around 100 megaflops probably, or I mean, actually not floating point, it will be quantized, so mega ops.
And then question on the test material. You're mentioning the licensing of that test material. Do you expect this to be part of the normative spec, and you're worried about whether or not we can reference it, or?
Yes, I mean, so the test I would see as part of normative, the normative spec. And yes, I don't know these license things good enough to understand whether that's an issue or not, that it's non-commercial.
Okay, yeah, for the notes, let's take another action for the chairs to check with ADs about licensing of some of these.
And I'm not familiar with how yours was created, but if it's not acceptable, there may be some opportunity to get it relicensed or something like that.
What is Creative Commons NC? What is the NC?
Non-commercial.
Non-commercial.
Non-commercial, yes.
Yeah. Well,
What is SWB? Sorry.
super wideband.
Oh, super wideband.
It's not full band. Yeah.
Okay. And that's it?
That's it, yes. Thank you.
Other questions? Thank you, Jan. Jean-Marc, you're
Thanks.
back up.
Can you share again?
And now we're on this one.
Great. So this is the scalable quality extension for the Opus codec, also known now as Opus HD. We're at version 03 of this individual draft. Next slide, please. So just a quick recap, there's nothing new here. So the idea of this extension is to lift some of the limits of the original Opus bitstream. So support for more than 8 bits of depth per band, support for wider than 20 kilohertz of bandwidth, and more than 50 kilobits per second per channel. Sorry, support up to 50 kilobits per channel. It was previously 250. And of course, we want to keep compatibility forwards and backwards with the original RFC 6760. Next slide. So the payload, again, this is exactly what I described the last time. We have a long extension ID, and it's currently 124 until we get a permanent one. The payload is entirely entropy coded, and essentially we add a bunch of refinement symbols that increase our resolution on fine energy, PVQ, and so on, to give us this higher quality layer. So next slide, please. Okay, now the actual update. It is actually this one in the latest draft. It's about 2 weeks ago. So the main change that has happened is around conformance. In terms of the format, by the way, the format itself has not changed since last IETF, so it's getting pretty stable. There's been a bunch of bug fixes to the reference implementation, but it's still fully compatible with 4 months ago. So yeah, so we now have some test vector material. It's all 96 kilohertz. It's floating point audio because 24-bit audio and so on. So using floating point audio is just the simplest thing to do with the test vectors. So we have in the new test vectors for Opus HD, we have 3 synthetic clips. One that has a sine sleeve that goes all the way from 10 or 20 hertz all the way to 48 kilohertz. There's a test with noise, and there's a test with just like impulses to make sure that transients are handled correctly. There's also 1 speech file and 2 music files that have been synthetically extended to 96 kilohertz for these test vectors, because finding actual 96 kilohertz microphone recordings is hard. And so in terms of conformance test, there's a strict conformance test for the decoder, and we propose a non-normative encoder conformance that is just like, again, we can discuss option, may or should on that. So next slide, please. So in terms of decoder conformance, I mentioned earlier these 6 test vectors. We encode them twice in the test vectors. Once they're encoded at essentially 1 megabit per second stereo, so 512 kilobits per channel. And we also have a fuzzing encoding that scans between 180 and 1.5 megabits per second. And the fuzzing encoder will just like use all kinds of random modes, not in a way that necessarily sounds good, but just trying to exercise the bit stream. And so we have this QEXT compare tool that is meant to compare the output for each of these test vectors, so 2 sets of 6. And for each of them, they have to be within a certain threshold using all 3 of the metrics from QEXT compare. QEXT compare is very similar to Opus compare, so it outputs a sort of error 4 term, which is like a 4th power RMS, and error 16, which is a 16th power RMS like on the actual spectrum. Very similar to what Opus compare did, and the RMS metric is just like time domain RMS, making sure that the time domain signal is very close. So each of those must be within a pretty strict threshold. And the threshold is even stricter for the first set, which is meant to be high quality as opposed to just like the random bit stream. So that's for the decoder, and we must still also pass the original Opus test vectors at 96. So we also provide a 96 decode of the original test vectors. So that's for the decoder conformance, which is a must. Now for the encoder, so encoders are harder to evaluate. Like even if you implement the encoder in exactly the same way, just like rounding error can cause like very different outputs, so we can't be as strict. But the idea there is to have, again, this QEXT compare tool with just like looser thresholds. And we run these original, for the same 6 test vectors, we have the clean, you run the encoder, you're supposed to run the reference decoder, and then you compare. And you have, there's again, some fixed set of thresholds that are supposed to tell you whether your encoder is correct. The only difference with the decoder is the RMS value the time domain RMS depends on the vector, because for things like a sine sweep, you can get to very, very small RMS with an encoder. For noise, there's like, Shannon channel capacity limits and so on. That means you're never going to get closer than a certain amount. So these RMS values differ between the different test vectors. And also, like, a listening test is recommended. The listening test here is not trivial because we want to show transparency, either with an ABX or a BS 1116 test. But essentially what that amounts to is proving the null hypothesis, which one cannot prove. So, it's going to be more around things like essentially your test needs to fail at detecting with like this much, this many samples or something like that. I'm open to suggestions here, but it's not going to be as clear cut as what you would normally do for a listening test. Next slide. So status of the whole thing. So the latest version is in the Opus repo, the EXP QEXT-MR branch. The code there still achieves minus 115 dB THD plus noise at 480 kilobits per second per channel. I provided a link to the test vectors in there, and the QEXT compare tool is part of the code that's on the branch. There's also now a similar shell script. I think it's called run Opus HD vectors that will actually check the decoder vectors, the fuzzing decoder vectors, and the original test vectors. There's no script right now for the encoder. And these have been tuned also to make sure that the floating point implementation actually passes the test vectors. At this point, the main thing we'll need to iron out is exactly the listening test details, but that's going to be a should anyway. So at this point, I think this draft should be ready for adoption by the working group, but you guys tell me.
Yeah, I think that we should do a adoption call on the list for it.
Yeah, apologies. We the last meeting we did ask in the room, and there was no opposition to adopting it then, and we thought we would run the adoption call before Madrid, but chairs dropped the ball, and we should have done that adoption call on the list sooner. But it looks like you've made a lot of progress since then, so even more ammunition now to get this approved as a working group document. So we'll start the list confirmation. No objections in the room for adoption? Does this work interesting for people? Okay, I see some thumbs up, and no objections, so we'll take the confirmation to the list this week and run a 2 or 3 week call on the list, but we should hopefully get this adopted well before the next meeting.
Thanks.
Thank you, Jean-Marc. Okay, Laura? Now, this is going to be interesting from the chair point of view, because I'm going to try to, actually, I think I can still share the slides on Meet Echo and do the audio from here. Let me see if that actually works.
What? Somebody presenting in the room? In this group?
Yeah.
Feel free to relocate the microphone.
Yeah, a little bit.
Okay, we can definitely hear that. Oh, no.
Okay.
So this mic is going to echo.
Well, we can.
Hello. Mhm.
You could be playing back sound from your own computer.
Okay. Oh, so he meant mute the speaker, not mute the mic.
Yeah.
Okay. All right. So I think we're good to go.
Can people on the call hear the remotely hear the ticking sound that we were just making?
Yes, I can.
Excellent.
Okay, so my name is Laura, and I'm here to present a draft on a comprehensive listening test battery for codec evaluation, specifically for generative codecs. We've initially thought particularly of DREAD, but during this meeting, I've also realized many other applications really, for example, for bandwidth extension, I can mention as we go. So I'm presenting also on behalf of my colleague Kamil Wojcicki, who is joining remotely. And let's get this started. Thank you. So I think the motivation by now with these talks leading up is quite clear. There needs to be some sort of subjective evaluation for generative models, for DREAD specifically. And generative models really bear some really new challenges in evaluation, both for objective metrics and for human listening tests. So for objective metrics, I think everyone's aware that, you know, they might still give you good insights, but we just can't guarantee how reliable and generalizable they really are. But also with human listening tests, people do raise concerns again and again, particularly if they're crowdsourced tests. And a few of these concerns we would like to address because we really think there are good approaches to doing this, and we would like to put forth a proposal for that. So one concern that has recently been mentioned in a publication is that absolute category ratings that are often used to produce MOS tests are reference-free, and this really can be an issue because there are range equalizing biases in these tests. So depending on what conditions and what qualities of samples are included in a particular test and a participant is exposed to, their perception, their expectation of a range, of a quality range, can really differ, and therefore their scoring can really differ a lot. We propose to implement a reference-based solution. So for clean speech, we would use a Mushra-like approach with a single stimulus evaluated at a time. I will go into more detail what that means in a second. And then for noisy inputs, for real-world inputs where there's no clean reference available, we propose degradation category rating. And this already brings me to the second point, that both clean and noisy speech should be tested. Jean-Marc kind of alluded to this, that he's training DREAD for this, but it may or may not be applicable in a certain application, whether that's needed. But I think it really is a good, it's good procedure, I think, to at least know what happens, even if you decide we're okay with poorer performance on noisy speech or reverberant speech. At least it should be clear what happens in these conditions. And then we also add intelligibility testing, which is not currently part of, for example, P808.
Would you also be looking at like double talk or crosstalk and the like, more than one person speaking at a time?
Mm-hmm. Yes, so not today, but it is at the very end in our slides, yes, to see what happens when two people talk simultaneously. Next slide, please. So this is what we're going to talk about today. So clean speech, quality evaluation with this Mushra 1S that I'm going to elaborate on in a second, and then real-world inputs with, in our case, relatively mild reverberation and noise, evaluated with DMOS, and then clean inputs for intelligibility test, the diagnostic rhyme test, which assesses intelligibility at the phoneme level. The data that we're using will in the future be open sourced as part of the forthcoming low resource audio codec challenge. So by the time of the next meeting, this should be publicly available already. So the conditions tested to illustrate this test battery really are based on single channel 16 kilohertz 16-bit inputs, and we level normalized them for speech to be at approximately a level of -23 to -26 RMS-dB. And the codecs that we tested are Opus wideband with the basic complexity at 6 kilobits and 9 kilobits, and also at 9 kilobits with lace and with no lace. And then we tested a DRED standalone version that Ahmed Mustafa very kindly made available for us at 0.5, 1, and 2 kilobit per second. The input files, so for example, a clean speech or a real-world reverberant speech and noise, were used as the reference in the respective tests. And sorry, I hope for people online this is not so overlaid, I don't know. We ran all these tests on Prolific, and the draft itself also contains more details on specific filters used. Okay, coming to the speech quality assessment. So let me explain a bit what I mean with Mushra 1S and why this perhaps slightly unorthodox way of running a Mushra test. So MOS tests are really convenient because they scale really well, right? We can run them at a pretty cheap cost in crowdsourcing environments, and they're straightforward tests, and we can add more conditions later if we want. But it suffers from these range equalizing biases. There's interesting studies from the field of TTS, for example, done where if you only include high quality conditions, you get a very different use of the scale than say you have a really bad system ranging to a really high quality system. Mushra, on the other hand, is very consistent, very sensitive to small differences in a great test, but it's also limited in the number of conditions you can test simultaneously because humans are limited in their capacity, and I think the official ITU guideline is to not surpass a number of 12 stimuli, which I think is already a lot even for experts, but in a crowdsourcing environment, I don't think it's feasible to test more than 4 or 5 conditions. And even then, if you have a test of 5 conditions and you want to add another condition to it, then you kind of need to rerun certain other conditions that you've tested because they kind of influence each other if they're in one test. So if 2 very similar systems are in a test together, people might perceive very fine differences and might try and amplify this on the scale. So it's great if you want to know about these tiny differences, but it doesn't scale very well. So an approach where we use only one stimulus at a time with the fixed anchor and the reference scales very well. And we have a clear range of expectation bound by the anchor and the reference. And it is a simplified task that can be run on crowdsourcing platforms. It is more sensitive than MOS due to this fixed range, and it is perhaps slightly less sensitive than Mushra because we're lacking the direct comparison. But we think it's a good compromise in the end. So we find it very useful, and let's look at some results. So just to reiterate, the DRED versions that we tested here are before any of the recent enhancements were made. So we see that DRED 0.5 is quite comparable in a way to Opus 6 in terms of quality and clean. And then we have staged improvements for DRED 1, Opus 9, and DRED 2. And then with lace and no lace, we see further improvements. I hope this is kind of in line with what people expect. For us, it was kind of a confirmation of what we expected from our own listening. So we see within Dread and within Opus, we nicely see this bitrate improvements in quality. And yeah, for Opus, we thought this was what is expected as well. So for these tests, Opus 6 was used as the anchor. Okay, let's come to the real world data. So we think it's important because not everyone might choose to have this kind of perfect input data, or might not want to take away, for example, reverberation. I mean, noise is often maybe undesirable, but reverberation can also be desirable. So we would like to test, or we wanted to test this, and chose the degradation category test instead of, again, an absolute category rating, because we can use a reference, even if this is noisy or reverberant. And the scale we use is the typical DMOS scale, also, for example, mentioned in ITUP 808.
Jean-Marc, you have a question?
Yeah, I'm just unsure about the real world condition claim there, because essentially it's, I don't, not sure what you're targeting in practice. Like, it seems to me like nowadays, pretty much every single client ever uses at least some sort of speech enhancement, and now it's mostly ML-based speech enhancement. I think, you know, WebEx, Google Meet definitely does, Microsoft Teams, and so on. So or do you see any particular cases where, you know, people still leave out the noise and reverberation?
I mean, these speech enhancement modules might not be perfect, so there might still be some residue of reverb and noise, but also it might not always be the target, right? So there are typically different modes that you can choose, and if you have a transparency mode, then it should be probably supported, or if not, at least we should know what happens, right? So if we know doesn't work so well for a transparency mode where there is a lot of noise, or if there's some noise, then I think it should be, there should be a way to measure it, and there should be basically its disclaimer. You know, if you use it in these conditions, performance might be more degraded. I think that's the point.
Jean-Marc, I thought you actually tried to do dread in these conditions because you thought it may be relevant, and then even tried to remove the degradations inside of dread itself, but it just wasn't feasible. So do you think that work was irrelevant, or when you went down that path, you thought it was relevant at first, but then you thought it was irrelevant at the end?
Oh, just to be clear, so my thought here is we should totally measure it. You know, that's good. I don't think we should care very much about it, but at the same time, if we can improve it without hurting anything else, why not do it? But I wouldn't go with, like, I wouldn't sacrifice anything to get better noise, but if I can get it for free, I'm totally gonna get it. That's my position here.
Yeah, Jonathan Lennox, I mean, there is, you know, what's called original sound or whatever that they do. And, you know, typically for people doing things other than voice, like, you know, which, you know, I'd be curious. I mean, probably Dread doesn't do great recovering from, you know, somebody singing, or worse, you know, electric guitar, but I'd be curious to see what it does.
But even in, for example, let's say in a call, a conference call in a meeting room, maybe you do want some of the noise preserved. Maybe you do want some of the reverb preserved to kind of give a more authentic feel of the room. So there's different ways of doing it, and I think, yeah, it should be, people should be able to know what is happening if they use this kind of mode.
Jean-Marc, was my understanding correct that the problem with training the Dread to deverberate was that that as it cut back and forth with Opus, it just, the difference between the two sounded bad? Is that what the issue was there?
Yes, essentially what you end up with if you train to remove noise, then you have this noise. The Opus is sorry. When you code with Opus, you get the noise, and suddenly Dread kicks in. The noise gets the noise gets removed, so suddenly the level goes down, and then it goes up again the next frame and down again, and so on, and it becomes like a really choppy signal. So that's really a no-go. Not just with Dread, like with anything. Although again, like in practice, I think what would actually happen is people would just like remove it to begin with. So you don't need to remove it in Dread. But it was kind of an interesting experiment to make just to see what it would give, and it's not a good result. At least we know.
Yeah, next slide. And I mean, just to be very clear about this, I'm not here to tell anyone, like, oh, this should be improved or anything. I'm here to present what we find and give people tools. So the interesting case, I think, in what we see in the quality evaluation here with real world data is that we still see a very similar ordering, but we see that Dread at 1 and 2 kilobits per second is now below Opus 9, where Opus 9 was in between them in the clean conditions. So perhaps Opus 2 is a bit, Dread 2, sorry, kilobit per second is a bit low in comparison and shows just a little bit less resilience to this noise. Of course, this test doesn't evaluate, noise removal or anything. It's just purely, does the presence of noise or reverb harm the output of the codec? But otherwise, we see a very similar pattern, similar ranking. Opus 6 and Dread 0.5, they're still really comparable. And then otherwise, we see expected patterns. So this is the only kind of anomaly that we maybe saw. I think we can jump to the next. We can listen to an example. So if we listen to the top, that's kind of a failure case illustrating this. I mean, this is cherry picked, right? To illustrate a failure case for Dread. And for people to understand what we mean with it's not really resilient on average. So this is an extreme case. Let's start from the lowest score.
This is Dread 2K.
Choose. We all should have an apple every day.
Okay.
Choose. We all should have an apple every day.
Can you point out which one you're playing, because we can't see here?
Oh, sorry. I started off with the 2K. Now I'm at the one. That was 2K followed by 1K, and now here's 500 bits.
Choose. We all should have an apple every day.
And here's Opus.
Choose. We all should have an apple every day.
And here's Raw.
Choose. We all should have an apple every day.
So I don't know. I don't think in this room it comes across exactly like you would hear it with headphones. Maybe at home it was better. I'm not sure. But in this example, if you have headphones, it's quite clear that Opus does a pretty good reconstruction job of both speech and noise, relatively few artifacts, and then Dread, with the rate going down, has some maybe slight slurring of speech. And of course, this is not necessarily an issue, right? Because it's just redundancy. But it's good to know about what happens. With Dread 2, there's also a little bit of noise added. So this is the risk, right? This is the risk of generative models. We can listen maybe to the last example as well, which shows the benefit of generative models. I mean, maybe we can listen in the order that they are. It's maybe easier.
You go to reverberant female?
Yeah.
Okay, so This is reverberant female at dread at 0.5K.
From out of the garden here, I can see the beautiful green lawn and some trees.
And now, no, I was doing lowest quality to highest quality because the raw may bias what you expect to hear. Now it's 2.2. I'm going in worst quality order, so you don't know the perfection until you hear it.
From out of the garden here, I can see a beautiful green lawn and some trees.
Now dread 1. Okay.
From out of the garden here, I can see a beautiful green lawn and some trees.
Dread 2K.
From out of the garden here, I can see a beautiful green lawn and some trees.
So here, by the way, we have made the slide deck available also in a repo. Perhaps Camille can post the link to it in the chat, and people can listen after the.
Yeah, in the meeting slides, I also posted the full PowerPoint, so you can play offline the audio on your own headsets.
Nice.
Offline.
Awesome, yeah. But I think in this example, it's quite clear that Dread 2 has really excellent quality and much fewer noisy artifacts than Opus 9. So,
You want the raw?
From out of the garden here, I can see a beautiful green lawn and some trees.
All right. Okay, let's move on. Now I would like to talk about speech intelligibility assessment, and this is really a.
Jean-Marc, are you still in the queue, or is that left over?
Yeah, no, I was just joining just to make a comment about. It was also in the first slide. So the characterization of dread as a generative model, I think, for the most part, it is not generative, in the sense that the coding part, the part that's in the bit stream is actually fully deterministic. The dread autoencoder is entirely deterministic, the way it's trained as well. The only part that is close to being generative is the vocoder part, but even that is being treated as a deterministic model in the way we standardize it with the test vectors, and even in the way we train it, because it's meant to mostly match a spectrum. So the amount of generation it can do, or the amount of hallucinating or anything like that they can do, is very, very limited by its size and also by its training. So.
Fair enough.
And I think in general, it's like the stuff about, noise and reverb is just like common to any time you attempt to go to lower bit rate by assuming characteristics of the voice. That is true for most audio codecs that have been designed classical or neural.
Mm-hmm. Yep. So going to speech intelligibility assessments, we work with the diagnostic rhyme test here, a simple test where the listener plays back one audio file of a single syllable word typically, and is presented with two alternative transcriptions and has to say which one they perceived. It's an ITU recommended method assessing phoneme level intelligibility. And it has many great advantages, particularly for crowdsourced testing, because there's no context effects. So it's really quite sensitive to any phoneme level changes that in a transcription task, for example, would be completely glossed over by context, or even in semantically unpredictable sentences. It can sometimes happen that you have context effects just because certain words can only appear in certain parts of the sentence. There's also no real learning effect, because these short words, the recordings, they're not particularly memorable like a full sentence would be. So there's no harm in reusing them. The participant doesn't know which one was correct. They might sound different every time, actually, depending on how they're processed. And we've successfully demonstrated this adaptation for crowdsourcing previously. The test vectors in several languages are open sourced, along with software to set up a test. Here are the results in clean. And for the really high quality models, we actually see that the ceiling is kind of almost reached. We're very close to clean intelligibility. So we would like to also run this in noisy conditions.
Jean-Marc, go ahead.
Yes, just a question, because I'm not familiar with this methodology, but it seems pretty interesting. Would my assumption be correct in thinking that this would be essentially kind of a lower bound on the word error rate you would get with a complete sentence where you have, words that are not necessarily too similar, or you have some context and all? Is that a reasonable assumption to make?
A lower bound on, sorry, I don't know what you mean by a lower bound on it.
Do you mean
That if you were to,
Do you mean word out of context?
like, if you were to test with, complete sentences and so on, it seems to me like you should get a word error rate that follows roughly this, but maybe a little bit higher because you have the context and not necessarily words that are very close to each other.
Yeah. I mean, it should give roughly comparable rankings, but word error rate, if you have transcription tasks, for example, they're just not as sensitive. So even if you have these matrix sentences, it's often, there's often a certain amount of guessing that will give you the right answer based on, what is happening.
I'm just trying to relate that to, let me actually ask.
Give you the opposite result. Yeah.
Okay. Or let me actually ask my question in a more direct way. Like, what do you consider to be the level where you have like decent intelligibility, or where does like conversation completely breaks down? Like, what would be the sort of percentage threshold?
Yeah. So I don't come with a recommendation of a threshold, unfortunately. I think it really depends a lot on the purpose. So, for example, for dread, which is used in in redundancy situations, I would lower the threshold of what I find acceptable, because it's just for a short time and wouldn't hopefully affect a whole conversation, even if it was impaired. But this is the way to measure it, right? How much? And if there is a model that you're currently training, is it better or worse? Is it the same? I think making decisions about what is acceptable really depends so much on the use case. I don't come with a global, this is the cutoff.
Okay. No, I would just be curious to see, like, if you, for example, if you tried to hold a conversation with a system that had a certain thing, like at which point are people giving up? Essentially, I would be curious.
No, that would be very interesting. I can't relate that exactly to these scores, to be honest, at this point. But it would be interesting.
Yusuf?
Yeah. Just a comment. In this dynamic rhyme test, usually there are broad phonetic groups, and you are just changing a single phoneme there, and it gives you better chance of analyzing exactly where your codec is having a trouble with. So instead of looking over a very global average metric, this kind of test is more useful to look at the details and understand exactly where your codec is good and where it fails.
Yeah, thank you. Yes, this is actually where we're heading next. So there's these
One more question from Camille, I think.
Okay,
oh no, he dropped out. Oh, he's back.
Hang on. Yeah. Can you guys hear me? Sorry.
Yes.
Yeah. So this is way more sensitive. This doesn't consider any context effects. I think Jean-Marc was asking about that. So in actual sentencing, in actual conversation, a lot of the confusions that happen here would be corrected naturally. So yes, this is kind of lower bound or lower than than lower bound in actual conversation. So it's extremely sensitive. It's extremely diagnostic, and Laura will cover that in a second. It's useful for that, but it completely ignores context and natural conversation types of issues that are present in real life communication.
Next slide.
Yeah, next slide, please. So we can look at these broad categories. So one of them, maybe the most relatable, is voicing. So, you have voice and voiceless consonants. But you can also look at it on a even smaller scale and have phoneme pairs. So on the x-axis, we have the ground truth phoneme, and on the y-axis, the alternative, which is the kind of like a decoy that is presented in this phoneme pair. And in this case, we've subtracted the Opus 9 scores from the DREAD 2K scores and get a delta phoneme score. So maybe look at this again later in more detail because it takes a little time maybe to process properly. But to cut a long story short, a negative score shows a degradation of DREAD 2 compared to Opus 9, and a blue score shows an improvement. So here we can see both. We can also see, we can use clean as the comparison and then see, okay, what phonemes do we degrade on? You can do all kinds of comparisons with this and really go into detail. But also these phonetic classes can be really useful. I have a backup slide if we want to get into that for voicing, where we see kind of a change into one direction, but not necessarily into the other. I think there's another question.
I just wanted to clarify. So this would be, you computed the confusion matrix for Opus 9 and the confusion matrix for DREAD 2, and you subtracted the two matrices one. Okay, great. Thanks.
Yeah, that's correct. That's correct. Yeah. Mm-hmm. And let's listen to an example. And here it's really quite important to start from the worst because it really, you can be easily biased.
Minus 60, this one?
Yeah.
Okay, so this is DREAD 2K.
Lead,
I'll play it again.
Maybe again, yeah.
lead,
Now DREAD 1K.
lead,
Again.
lead,
DREAD 0.5.
lead, lead,
Opus 9.
lead, lead,
And raw, clean.
lead, lead,
Here's 0.5 again.
lead, lead,
Here's 1.
lead, lead.
To me, subjectively, 0.5 sounds worse.
Worse. 0.5 is the only one I heard is the.
So I think it's really worth going back with headphones because there's two different components, right? There's the quality and there's the actual sound that you hear in terms of the phonetics. And if you listen to 0.5, it's worse quality, but it's actually maybe slightly closer to the lib phoneme. It's kind of it's just a bit ambiguous. Whereas DREAD 2 is great quality, but is very decisively live. It's so hard to tell in this room. This room has some reverb.
We're adding reverb to the.
Yeah. So please, I encourage you, go back and listen. The last example has also, quite, it's a minus 100 for DREAD 0.5, so that is quite decisive. It 100% confused everyone, and everyone said it's
So this is
the opposite.
DREAD got. DREAD 0.5 got.
Yeah.
That sounds like a Russian yes.
So yeah. So these things, and in
Got
that
it.
sense, sorry, in that sense, there is a generative component, even if perhaps it's not the most generative model. So perhaps something like bandwidth extension is even more generative because it's actually making up stuff, right, that isn't there. So for bandwidth extension, I think this could also be a really useful use case, this test. But yeah, but also in dread, we do see things that, I would classify as a hallucination. Whether this is necessarily impacting communication is a different question, because our brain corrects a lot of things, and from context, we can usually disambiguate.
I mean, if the argument is context, I would say we don't need any of this, right? Because you can drop half the words and make everything out. So, but I don't think we would accept the codec that drops half of the words.
I do think it's extremely interesting in the sense that, like, the audio quality is really kind of irrelevant for the dread use case. What's important is intelligibility, and this is more directly a test of intelligibility than.
We have Camille, go ahead.
Yeah, I completely agree. There are use cases where intelligibility, the context is limited. So like if somebody is saying digits for a phone number, or saying their name, and you cause a confusion on, say, first letter or last letter of their name, then this would be impactful real life case where this would cause an impact. Other confusions on intelligibility caused here that are detected by this test will be recovered from context, but some won't be.
Yeah.
Jean-Marc?
Just pointing out the error here is actually not a generative type error, but rather just like a fully classical, you don't have quite enough resolution in your quantizer and you're sort of matching the wrong thing. Like vector quantizers will do the same kind of thing if you drive them to low enough bit rate. Like if you had like a classical 500 bits per second vocoder based on GMMs back then, they would make this kind of error as well. It's just like collapsing the space, fully deterministic.
Okay.
Camille, you had something else?
Yeah. So so Fargan is trained with adversarial fashion.
So Fargan has a very small adversarial component, but it's not the one that's responsible for any confusion there. Essentially, all of it is just due to the feature quantization. Fargan, again, like this is what I presented in the test vectors. Fargan will actually always reproduce the spectrum that you give it, as in terms of features. Like its features is like classical capstrum plus pitch. I believe in at least one of these cases, like the G versus the D is probably just like the pitch voicing that probably got quantized too coarsely, and it just decided that it wasn't voiced. And if you devoice, then you end up with a D.
I think if I understand Jean-Marc's point, it's like we're not going to see hallucinations between yes and no. It's not going to be like 6 fingers or 2 fingers, in video hallucinations, but things that may be close. That kind of traditional fuzzing would still be a problem. Not a dramatic hallucination, but can or can't. That's a giant difference, right? That's a yes or no equivalent. But can or can't could be close enough to cause a problem in some of these.
That's actually.
I mean, you have those confusions even without a codec. Like people will, you say one, you understand the other. So you add a codec, you always add a little bit of confusion. Any distortion you add adds to that. In the case of dread, you have this quantizer. It's a bunch of scalar quantizers, so it snaps, just one notch off, and you get a slight change there. that's also the reason why we have this variable bit rate in the within the redundancy packet, where everything more recent that's more likely to be used uses a higher bit rate, and as you go back in time, the bit rate is actually lower. So to maximize the use of the bit allocation. But it's entirely just like deterministic quantization issues there.
So maybe then in the future, I mean, the useful part of this, of methods that rely more heavily on or have generative component to them is in really adverse conditions, if you're trying to improve intelligibility, where some speech content was destroyed and is gone, and you're trying to reconstruct it. And maybe those generative approaches have the potential to do that, but they could also have a greater potential to cause adverse effects. So there, this methodology would be useful.
Yeah, I mean, that's also why even if you look, for example, at pure PLC in Opus, which is not what we're talking about here, like this is DREAD, but if you look at how the pure PLC is done in Opus now with the machine learning model, the feature predictor is on purpose not generative, it's predictive. So if it's hesitating between it could be this or this phoneme, it's going to pick right in between, which is going to cause a weird phoneme that's halfway in between instead of picking one. And the only thing that's pseudo-generative is the vocoder, but the vocoder just synthesizes exactly what it's been told to synthesize. So it's not making things up. That's the whole purpose, to never make up audio there, because that would be dangerous.
I guess a question would be are there cases where the vocoder with unquantized data was producing intelligibility problems via this sort of test? And that's not a case that we tested, an uncoded case. But it would be, I think, interesting to know if the Fargan was causing some confusion, and that would potentially be a generative kind of error in that case.
Yeah, that would be interesting to see. Personally, playing around with Fargan, I've not observed that. One actual interesting thing with Fargan compared to other vocoders that I'm aware of is the impact of the adversarial training is incredibly small. And that if you train it without adversarial training with purely predictive loss on the spectrum, it already gives you a good vocoder. And the only thing that the adversarial training does, it doesn't really meaningfully increase the spectral error. All it does is it makes it sound very slightly less metallic or something. But the adversarial impact is tiny.
Jan?
Yes. So very interesting results. Thanks a lot. So that quite insightful. One thing that I'm having difficulties with this testing approach is that I find it very hard to translate this into what would actually happen when using DREAD. So I'm curious why this testing as a standalone. It's kind of, it puts things under a magnifying glass, that I understand, but still, if you want to know how DREAD performs, then you wouldn't be the natural thing to do to test it in action with error patterns and so on, because I mean, usually you would see only very short chunks that are coded by DREAD, and I mean, the quality seems to be on acceptable level, which is similar to what people are doing today. If you have LBRR, so you code at a lower quality because kind of the thing that you compare against is just not having that information. Also, I mean, the very low bit rate that at the moment with the setting that's only used if you have very long losses, so it's kind of used more rarely than the higher bit rates. So I mean, while I find this really interesting, the results, I'm wondering, whether this is really the right way of looking at this. And also, I mean, DMOS, it's kind of it's more precise and so on, but I think especially for communication, people tend to use absolute category rating because that's more like the actual situation, because you don't have a reference if you are on the phone. So just some questions, but I mean, as I said,
No, I mean,
pretty interesting.
No, I agree. So as I said, I don't come here to say, oh, this is a bad score. You need to change DREAD, right? So this is not what I'm coming here for. I'm providing tools to see and to have information to then decide, great, we're happy with this for this use case, and this is what we're going to go with. Certain cases, maybe like the use in noisy conditions, maybe we can put a disclaimer on things and say, hey, you'd be better off with a speech enhancement tool in front. Things like this. I think they're valuable insights. But yeah, it's just, knowledge is power. The more you know, I think personally, the better.
Yeah, I completely agree. I was just I mean, the title is like test battery. That sounds like it's a complete thing that you need to test the whole thing.
No, I don't think we necessarily come with the intention to, make this, oh, you need to pass these tests and fulfill certain criteria in order to pass. But say someone was developing a new version of DREAD, then there should be methods to say, is it better or is it worse or is it the same, right? So, and I think this is just a comprehensive approach. You're completely right. I ignored the obvious elephant in the room, what happens in packet loss situations, right? So we just saw that there was some testing done on this before. So we wanted to present something that hasn't been done before to provide more tools kind of for that as well. But on the next slide, you would have seen that we would like to test this in the future and would like specific input from the working group on which specific scenarios, which specific loss rates and loss patterns, and would people prefer synthetic testing or on real world losses and so on. There's just so many variables that we would like your input.
We're at time, so let's keep our comments brief. So, go ahead, Jan.
Just one thing. So, because you said, I mean, whether a method is an improvement or not, I just also wanted to point out that it's kind of a multidimensional problem, and quality and intelligibility is one part. Complexity and size and such things are other parts. So it's kind of difficult to put things in linear order. Except if they really improve on all the axes, it's not not completely ordered. Okay, but that's just for me.
Always trade-offs to make, and I think this just provides more data points to make those decisions.
Okay. Thanks.
Okay. Yeah, Jonathan, my next actually was just raised a question, something that you mentioned about the what the unquantized vocoder would sound like. I was curious, how close is the 2 kilobits? How coarse is the 2 kilobit DREAD to unquantized? I mean, how coarse or fine is that quantizer at that point?
Even at 2 kilobits, the quantizer introduces more error than the vocoder.
Okay. And I mean, can you run it at higher than 2 kilobits, or is it just?
We could, but it kind of defeats the purpose of the redundancy. Yes, we could have any bit rate we like.
Cool.
Camille?
To Jan's comment about standalone, so we were thinking that standalone might be useful if somebody's reproducing a codec that was produced previously or added previously. So like if you want to add improvements or make changes, first thing you would do is you would retrain that baseline, and then the weights will be different, obviously. Maybe you can use objective metrics, but how do you compare, and how do you understand that you've reached similar level of intelligibility, quality, and then you are now good with your process, with your tools to make additional improvements? So standalone might be useful there. I'm not sure if you guys agree, but definitely the packet loss scenarios that where redundancy is used is the next thing on our agenda. We do need some guidance from your side, like Laura mentioned, which patterns to use, what settings to use in those tests. Yeah.
And also, if there are other conditions, I mean, we just did something here, right? We came with a lot of data already, but this wasn't necessarily requested. So if you have other codecs that you would like us to evaluate, if you, for example, this new version of Dread, we can run this and see. Hopefully we'll see this nice improvement on noisy data and similar quality on clean, maybe even better, as Jean-Marc indicated.
Jean-Marc?
Yep, I have just like a much higher level question. I'm curious about, so my question is about the document, like obviously with the actual work in there, that's quite useful as you presented a bunch of this, I hadn't seen before. But in terms of the document itself, I'm just curious what the purpose is. Is it just like a placeholder or way to publish your temporary results, or do you intend on having it eventually go through IETF process, in which case was your intention to make sort of requirements document or a document that shows how you should be testing codecs in the future, or a characterization of dread, or like what is the ultimate purpose of the document, if any?
Personally, I don't think we're necessarily set on anything. I don't think we would necessarily go so far as to make this as a forced requirement. But I do think that it has purpose as a recommendation and tools for people to use if they want to reproduce, if they want to improve components.
From a chair point of view, I mean, a lot of working groups start off with like requirements and then evaluation drafts. We didn't, because we kind of, I think, knew our requirements. We kind of did that in the charter for requirements, and we kind of trusted the drafts to do their own evaluation. But I think this is an interesting independent evaluation from some dimensions that people weren't necessarily thinking about. So I don't think we need to add a charter item for this or anything. I don't think we are going to have a formal evaluation draft that Codex must pass. But I think it's just interesting work that if we want to keep working on it, and like if Jean-Marc, if you'd be interested in whether or not the new version of Dread, changes any of these numbers, whether or not you'd like them to rerun some of these things on the new version, maybe that would be interesting. Or if there's other aspects of these tests or different kinds of tests that you think would be relevant, maybe we could progress the draft that way. But I think it's just informing the other work. I don't see it becoming a work group deliverable.
Okay. Right. Because I mean, in that case as well, like I wouldn't see an issue, for example, in at least some of it to become like their own section of the Dread document as characterization of Dread. And I think there's definitely very interesting data in there. Like, I think that's at least something worth considering.
The Dread document's rather not very normative on the exact behavior, and so there's a lot of room for implementers to do various things. So this is maybe an avenue to provide some better advice on testing practices for those better things.
Yusuf,
yep.
Do you have a final comment?
Since somehow I think that this test vector-based assessment of the quality might not be very sufficient. I feel like it leaves a lot of responsibility to the researchers to make their own subjective test, own assessments than the actual testing. And there is a lot of room for improvement on the testing of the new features, especially if there will be more additions like this bandwidth extension, etc. Of course, this has also its own difficulties. For example, if we are using crowdsourcing platform and running these tests, then different groups might have different implementations of their crowdsourcing platform, different filters, etc. And then the question of repeatability arises, and then maybe making even that framework as having a reference for that would be interesting.
Yeah. Okay.
But I think there's room for improvement in.
But just to clarify, I don't think all the test vectors are just like I said earlier, binary, yes, no. Did it fail miserably or is it okay? But none of them try to attempt to measure quality or comparative, like measuring, DREAD version 3 versus DREAD version 4. Nothing, both those test vectors will pass, but nothing will give you a comparative quality of did anything improve in any of those things. So I think a framework like this may help you get some insights into comparative things where the test vectors are not at all intended to qualitatively compare. They're just to pass.
Yeah, like the test vectors tell you whether you replicated the reference implementation. It doesn't say anything about whether the reference implementation was good. And these tests tell you that, whatever implementation is good. It doesn't tell you that it matches what it's supposed to match or it's compatible or anything. It's completely orthogonal goals, I think.
So we're 10 minutes after, so let's, any other final points before we wrap up? Okay, so for next steps, Laura, you think you have good feedback of what you want to do, or you want to consult with some of the other draft authors about what if anything, you want to do differently in your next rev?
Yeah, I mean, we would really be very grateful for input on specifics for packet loss testing.
Okay.
And yeah, any other conditions you would like to see.
Yeah, I'm happy to help.
Nice.
All right. Thank you, everyone. Apologies for going over. Enjoy the rest of your week. Thank you for the crazy hours for all of you remote attendees.